All right, so welcome to yet another lecture. And honestly, if you've ever worked on a microservices system, you've probably felt the exact pain we're going to solve today. Let me paint a quick picture for you. Imagine a mobile app trying to load a user's home screen. Simple, right? But behind the scenes, it's not simple at all. It needs the user profile, their recent orders, recommendations, notifications, and all of that data lives in completely different services. Now here's the catch. Without an API gateway, the mobile app itself has to call 4 different services, 4 separate network calls, 4 different endpoints, different authentication, different everything. And it doesn't stop there. Now think bigger. You have a web app, a mobile app, maybe even a third-party developer using your APIs. And all of them have to know about these internal services. And the moment you change or move even one service, boom, clients start breaking everywhere. It gets messy really fast. And that's exactly where the API Gateway comes in. It gives you a single front door, just one endpoint, one authentication layer. And behind the scenes, it handles routing, rate limiting, security, logging, basically all the heavy lifting. So instead of chaos, you get control. Now in this lecture, we're going to go step by step. You'll understand what an API gateway actually is, when you should use it, how cloud providers implement it, and also some common mistakes that can actually turn a gateway into a bottleneck, and which, trust me, happens more often than you think. All right, so with that said, let's jump in and start with the basics. What exactly is it? An API gateway is not just one single thing. It's actually a combination of 6 important responsibilities, all packed into one layer. So let's go through them one by one, and I'll keep it very simple. All right, first one, request routing. This is the most basic, but also the most important job. So when a request comes in, the gateway has to decide where it should go. It looks at things like the URL, the HTTP method, sometimes even headers, and then it forwards the request to the correct backend service. And here's the key idea. The client has no idea what's happening behind the scenes. It just calls one endpoint. It doesn't know that the user service is on one server and the order service is somewhere else. And then honestly, it doesn't care. The gateway hides all that complexity. Now second, authentication and authorization. So every single request passes through the gateway first, and the gateway checks, is this request valid? Is the JWT token correct? Is the API key valid? If not, boom, it gets rejected right there. It never even reaches your backend services. And this is actually powerful because now your microservices don't have to worry about authentication again and again. They can just assume, okay, whoever reached me is already verified, and they can focus only on business logic. Third, rate limiting and throttling. So basically, the gateway controls how many requests a user can make in a certain time. For example, a free user might only get 100 requests per minute, a premium user maybe 10,000, and an unauthenticated user maybe just 10 or something very small. So every request is checked, and the gateway makes sure nobody is abusing the system or overloading it. Simple idea, but super important in real systems. Now fourth, protocol translation, and this one is interesting. So different systems sometimes speak different protocols. For example, your mobile app might use REST APIs, but your internal services might be using gRPC because it's faster. So what happens? The API gateway sits in the middle and translates. So the mobile app sends a REST request to gateway, receives it to converts it into gRPC to sends it to the internal service to gets the response to converts it back to REST2 and sends it back to the app. And why do we do this? Because it keeps things clean. Clients stay simple, but backend systems can use whatever is most efficient internally. Now, fifth, load balancing. So the gateway doesn't just send traffic randomly, it actually knows about all running instances of a service. It spreads traffic across them evenly. And if one instance fails, it simply removes it from rotation. And even better, it can support things like canary deployments, where maybe 5% of traffic goes to a new version just to test it safely before rolling out fully. And finally, sixth, observability. So since every request passes through the gateway, it becomes the perfect place to observe everything. You can collect logs, metrics, traces, everything in one place. So you can actually see things like latency, error rates, traffic patterns across all APIs in a single dashboard. And honestly, this is what makes debugging and monitoring so much easier in production systems. So yeah, those are the 6 responsibilities of an API gateway. And once you see them together, you realize it's not just a router, it's really the control center of your entire system. All right, let me make this really concrete for you. I want you to clearly see the difference between before and after an API gateway. So first, without a gateway, this is where things start getting messy. Your mobile app needs data from 4 different services. And guess what? It now has 4 different service URLs hard-coded inside it. Everything is tightly coupled. Now imagine this. The user service moves to a new cluster. Maybe just a small infrastructure change. But boom, the mobile app breaks instantly because it was pointing to the old address. And what happens next? A bug gets raised, the backend team rushes in, they deploy a hotfix, and just like that, 2 days are gone, just because of a simple service move. Now it gets worse. Every client starts handling authentication in its own way. The mobile app validates JWTs slightly differently. The web app has its own variation. And the third-party SDK, it does something completely different. So now you don't have one auth system, you have 3. And that means 3 different places where security bugs can creep in. Honestly, that's a nightmare waiting to happen. And then there's rate limiting, or actually the lack of it. So imagine a buggy client or a bad retry loop. Suddenly, it starts hitting your order service with 10,000 requests per second. And because there's no central control, the service just gets overwhelmed. It crashes, and then everything downstream starts failing like a domino effect. Now debugging, that's another pain point. Logs are scattered everywhere, across 4 different services. So when a customer says, hey, something is broken, you literally have to piece together logs from multiple systems just to understand what happened. It's slow and painful. And here's something people often forget. Your internal architecture is completely exposed to the outside world. External clients actually know your internal service structure. User service, order service, recommendation service, everything. So if you ever want to reorganize or refactor things internally, you can't do it freely because external clients will break. Now, let's flip to the right side with a gateway. Everything becomes clean. Clients now talk to just one URL. That's it. The gateway takes care of routing. So even if a service moves, gets renamed, or even split into multiple services, clients don't even notice. Nothing breaks. Authentication, now it happens once, in one place, at the gateway. So instead of 3 different auth systems, you now have one central enforcement point. Much safer, much simpler. Rate limiting is also handled at the gateway level. So no single bad client can overwhelm your backend services anymore. The gateway protects everything behind it. And debugging becomes way easier too, because now all logs flow through one central place, the gateway. So when something goes wrong, you don't have to jump across 4 systems. You just look in one place. And finally, the biggest win. your internal architecture is now invisible to the outside world. Clients only know the gateway exists. They don't know and they don't care what's behind it, and that's powerful. Because now you can refactor, split, merge, redesign your services freely without breaking clients. So yeah, the API gateway is not just a convenience layer in a microservices system. It's actually foundational. Without it, things slowly become chaos. With it, you get control. Okay, so let me kind of ground this in real tools you are actually going to see in the industry, like in real jobs, right? Because till now we talked about concepts. Now let's connect it to actual products. So first, let's talk about Kong Gateway. So Kong Gateway is probably one of the most widely used open source API gateways out there. And the key idea, the thing you really need to remember, is its plugin architecture. So basically, everything in Kong is a plugin, like authentication, rate limiting, logging, request transformations, everything. You don't really code the gateway in a traditional way. You just kind of compose it like stacking plugins on top of each other. And because of that, it becomes very flexible, very modular. You'll see companies like NASDAQ using it for financial APIs, and even platforms like Robinhood using it for trading systems. So yeah, if you want maximum flexibility and you are not tied to a single cloud provider, Kong is honestly one of the strongest options out there. Now, second one, AWS API Gateway. So this one is very different. AWS API Gateway is basically what you use when you are deep into AWS and you just don't want to manage any infrastructure at all. Like zero servers, nothing. You define your API, you set up routes, and AWS just runs everything for you behind the scenes. And it integrates really nicely with Lambda. So you can literally go from an API endpoint to a serverless function in just a few minutes. It feels very smooth, very fast to build. But yeah, there are trade-offs. Sometimes it's hard to test locally. Cold starts in Lambda can add latency. And honestly, you are very tightly locked into the AWS ecosystem. So moving out later is not that easy. But still, if your goal is speed and you don't want to operate infrastructure, this is honestly a very solid choice. Now, third category, NGINX and Envoy. So here we are talking about performance. So tools like NGINX and Envoy are kind of like the performance kings, if I can say it that way. NGINX is insanely fast. It can handle millions of requests per second. And Envoy, well, Envoy is basically the backbone of modern service mesh systems. It powers things like Istio and Linkerd, sitting as the proxy layer handling all traffic. Both of them support modern protocols like gRPC and WebSocket out of the box. So if you are running Kubernetes and you need serious performance, your platform team will usually go with something like NGINX Ingress Controller or Envoy Proxy. But yeah, the trade-off is that they are not plug and play. You get more control, but you also have to configure more things manually. So more power, but also more responsibility. Now, finally, how do you choose between all of this? So if you are a cloud-native team, especially on AWS or GCP, just start with the managed gateway. It's the easiest path. If you want multi-cloud flexibility, or you are running on-prem systems, then Kong is usually a very good fit. And if you are building for extreme performance or you already have a service mesh set up, then Envoy or NGINX is usually the direction. So yeah, that's kind of the mental model. It's not about which one is best. It's more about what problem you are solving and what trade-offs you are okay with. Slide 5. 4. Gateway anti-patterns. A gateway done well is one of the most powerful patterns in distributed systems. A gateway done wrong is one of the most painful problems to fix. Let me save you from the 4 most common mistakes. Anti-pattern 1. The God gateway. This is when teams start adding business logic to the gateway. At first it seems reasonable. The gateway is already there, it already sees every request. Why not add a little logic? Then a little more. Then some aggregation, then some transformation. Before long, the gateway is doing the work of 3 services. It is a new monolith. You have traded one monolith for another, and this one is harder to test and deploy. The fix: gateways route, authenticate, and rate limit. That is it. Business logic belongs in services. Anti-pattern 2, synchronous fan-out. The gateway receives a request and makes 8 downstream service calls in sequence to build the response. Service 1 takes 50 milliseconds, Service 2 takes 30 milliseconds, Service 3 takes 80 milliseconds. Total response time 160 milliseconds plus overhead. And if Service 3 is having a bad day, everything waits. The fix: use the backend for front-end pattern, which we will cover in a later lecture, or use asynchronous parallel aggregation, never sequential chains. Anti-pattern 3, single point of failure. You deploy one gateway instance. It handles all traffic. When it crashes, and it will crash, everything stops. A well-designed gateway with no redundancy is more dangerous than no gateway at all, because it creates the illusion of infrastructure without the resilience. The fix: always multiple instances behind a load balancer, always circuit breakers. Anti-pattern 4, fat gateway, thin services. This is the slow version of the God gateway. Over months, the gateway accumulates logic, one small decision at a time. Services become thin, the gateway becomes the application. The fix: regular architecture reviews. Audit the gateway every quarter. If you find business logic, move it to a service. All right, so now let's talk about something really interesting, the backend for front-end pattern. So this idea, the backend for front-end pattern, or BFF, backend for front-end, is actually one of the most practical evolutions of the API Gateway concept. And fun fact, it was first popularized by SoundCloud, and now it's kind of widely used in big engineering organizations everywhere. So let's first understand the problem. The issue with a single general-purpose API gateway is that it tries to serve everyone in the same way. But in reality, mobile apps, web apps, and third-party developers, they are not the same at all. They have completely different needs. So for example, a mobile application needs very small payloads because bandwidth and performance matter. It also needs things like offline support and push notifications. Now compare that with a web application. A web app usually wants richer data, maybe server-side rendering support, and session-based authentication flows. And then you have third-party developers. They care about things like API key management, rate limiting, and a proper developer experience or portal. So now imagine you try to support all of this using one single gateway. What happens? Honestly, it becomes a compromise for everyone. Because if you optimize for mobile, web starts suffering. If you add features for third-party APIs, internal systems get affected. So yeah, one size fits all just doesn't work here. And this is exactly where the BFF pattern comes in. So instead of one gateway for everyone, you create separate backends for each front-end type. So you have a mobile BFF backend for front-end, which is fully optimized for mobile apps. It returns lightweight or lean payloads, handles push notification routing, and supports offline sync logic. Then you have a web BFF, which focuses on things like richer data structures and sometimes server-side rendering concerns. And then you have a third-party BFF, which is designed for external developers. So it handles API key management, strict rate limiting, and provides a clean public API experience. Now here's the important part. Behind all of these BFFs, the same backend microservices are still running. So you still have your user service, order service, payment service, all shared, nothing changes there. But the way each client interacts with them is completely different because each BFF is optimized for its own use case. And honestly, one of the biggest advantages of this pattern is team ownership. So the mobile team can fully own the mobile BFF. They can deploy changes independently without waiting for the web team or asking for approval from some central gateway team. And this is where something called Conway's Law comes in, which basically says that system design mirrors organizational structure. So here we are actually designing the architecture intentionally to match how teams work. And yeah, this pattern was originally invented by SoundCloud, then adopted by companies like Spotify, and even variants are used by Netflix. So clearly, this is not just theory. It's something that works at massive scale. So in short, if you have multiple types of clients and separate teams, the backend for front-end pattern is honestly one of the cleanest solutions you can use. Okay, so now let's talk about rate limiting. And honestly, this looks simple at first, but once you actually implement it in real systems at scale, you realize it's not simple at all because there are like 4 major algorithms and each one behaves very differently under load. So let's go one by one, slowly. First one, fixed window rate limiting. So in this approach, you divide time into fixed buckets. For example, 1-minute buckets. So the rule is something like 100 requests per minute. Simple, right? Very easy to implement, very easy to understand. But here's where the problem starts. So imagine this, at the end of minute 1, a client already made 100 requests. And then the clock resets, new minute starts. So immediately, the same client can again make 100 requests in the first few seconds. So what happens? At the boundary, the system actually allows 200 requests very quickly, even though the limit was supposed to be 100 per minute. And this is called the fixed window boundary burst problem. So yeah, simple idea, but not very accurate in real traffic patterns. Now, second, sliding window. So instead of fixed buckets, we look at the last 60 seconds from right now. So it's always a moving window, like a rolling time frame. At every request, you check how many requests happened in the last 60 seconds. This completely solves the boundary burst problem because there is no reset moment anymore. But the trade-off is you need to store timestamps of requests, which means more memory, more computation, so better accuracy, but slightly more expensive. Now third, token bucket algorithm. So this one is actually very popular in production systems. Imagine a bucket that slowly fills with tokens, let's say 10 tokens per second, and every request consumes 1 token. So if you have tokens, request is allowed. If you don't, request is rejected. Now here's the interesting part. If a client is idle for some time, tokens keep accumulating up to a maximum limit. So later, that client can suddenly make a burst of requests using saved tokens. And that's actually good, because real users don't send perfectly steady traffic. They send bursts. So this model feels very natural, very practical, and that's why most production AP is used token bucket. Now fourth, leaky bucket. So this one is a bit different mentally. Here, requests don't go directly for processing. They first go into a queue like a bucket filling up. And this bucket leaks at a constant rate, meaning requests are processed steadily no matter how fast they come in. So even if traffic spikes, the output stays smooth and controlled. But if the queue becomes full, new requests are just dropped. So the benefit is stability, very smooth traffic flow, but the downside is added latency because requests might sit in the queue before being processed. Now, finally, the recommendation part. So in most real systems, you use sliding window for standard public APs because it gives accurate control. You use token bucket when you want to allow premium users some flexibility, like short bursts. And one very important rule, always implement rate limiting at the API gateway level, not inside individual services. Because if you do it inside services, you lose the whole point of centralized control. So yeah, that's basically it. Rate limiting sounds simple, but in real systems, it's actually one of the most important and subtle design problems. Slide 8, action item. Okay, so now I have a very important action item for you from this lecture. And honestly, I don't want you to just think about it in your head. I really want you to draw it. Like physically draw it or use a whiteboard tool. Anything is fine. So here's what you do. Take a piece of paper or open a whiteboard app and draw your current system architecture. Start simple, draw your clients first. Mobile app, web app, maybe third-party clients, whatever applies to your system. Then draw your backend services, user service, order service, payment service, whatever you have. Just map it out visually. Now, once you have that, draw a second version. This time, add a proper API gateway layer in front of everything. So now all clients are talking to just one entry point, and the gateway is routing everything internally. And while you are drawing this, I want you to pause and ask yourself something very important. Which of the 6 gateway responsibilities are actually present in my system today? So, do you have authentication at the gateway level? Do you have rate limiting? Do you have centralized logging? Just go one by one, slowly. And for each one that is missing, write it down. And even more important, ask yourself, where is this responsibility living right now? Or does it not even exist at all? Because in many real systems, some of these things are just not implemented properly. Now, after that comes the design decision part. Ask yourself, do I really need one single general purpose API gateway? Or would the backend for front-end pattern actually fit better for my system? Think about your clients. If your mobile team and web team are constantly moving at different speeds and they need very different types of data, then honestly, BFF is usually the better choice. But if your system is simple, maybe just 1 or 2 client types, then a single API gateway is totally fine. Now, next step, rate limiting, you need to actually define it. So write down your tiers clearly. What does a free user get? What does a paid user get? What about internal services? Be very explicit and with like real numbers, not vague ideas. And then finally, one last thing, very important. Write an ADR, an architecture decision record for your gateway choice. So document it properly. Should you use Kong Gateway or AWS API Gateway or NGINX or something else? And use a simple structure, context, decision, alternatives, consequences, because this is not just theory, this is a real engineering decision, and it deserves to be written down properly. And yeah, in the next lecture, we're going to go one level deeper. We'll talk about API versioning, which is basically how you change your API over time without breaking all the clients depending on it. And trust me, this is where things get really interesting and a little tricky too. See you there.
Thank you so much for watching this. Before you go, please don't forget to subscribe to my YouTube channel and turn on the notification bell so you never miss any of my upcoming videos. I regularly share valuable lessons, practical tips, and step-by-step tutorials to help you improve and grow. And if you are serious about mastering software design and architecture and want a complete structured learning experience, so I have created a full course that includes detailed lessons, assignments, quizzes, and downloadable workbooks to help you practice and apply what you learn. So, if that sounds helpful, just check the link in the description below and enroll in the course today. I would love to see you inside and support you on your learning journey.